right, we're going to take some notes on seasons. So in your notebook, we'll put seasons on the left-hand side. You draw your line. And the first thing we want to note about seasons is they are caused by the tilt of the Earth as it orbits the Sun. So as the Earth revolves around the Sun, we're going to have different seasons because of the tilt. If we had no tilt, we would have the same season all throughout the entire year. It'd be more of like a fall or spring season. So this tilt, so this alters the intensity, so how bright the light is. So it alters the intensity at different locations. And alters the duration, or alters the daylight hours. And I'm going to put that in parentheses, duration, so we can remember that. All right, so we're going to have that in your notes right there. We're going to come back to that. I don't need you to draw this stuff, but I want to clarify something. So let's say this is our orbit for Earth. Pretty circular, slightly elliptical, but mostly circular. The Sun is not perfectly in the center of Earth. Instead, the Sun is slightly off center. So if this is the Sun, this is our star here in the center of our orbit. And this circle here represents the orbit of Earth as it moves. Okay, my bad. It actually goes counterclock. No, it's just right, counterclockwise. So our Earth will orbit around the Sun. Now we're always pointing the same direction in space. So as we go through our orbit, that tilt is going to cause us to be pointing towards the Sun in this location maybe, and pointing away from in another location. Now, here's a problem. A lot of you learned that the tilt of the Earth causes us to have seasons. Because, let's say, if the Sun's rays are most intense here, this part of the Earth has tilted toward the Sun, and therefore the tilt causes us to be closer to the Sun because of that tilt. So let's say if this was summertime, here is us here, this is northern hemisphere. Now we are closer to the Sun in this season than we are in this other season, causing us to be cold and have it be wintertime. However, this is very, very, very untrue. It all has to do with the intensity, that thing we were measuring the other day in our lab. The intensity of light is going to be different. Now, one of the ways I say this isn't, you're like, oh, it looks like it got closer, you know, because this is definitely a smaller distance than this long distance here, but it's not, and I'll explain why it's not. So even though we would turn towards the Sun and turn away from the Sun, so let's say here that this shows winter, and this position shows summer. Summer is our hot time. It's when we have the longest daylight hours starting on the solstice, and then it's just we have a lot more heat during the summer. Here, this distance is a lot further of a distance than the distance in winter. So when we are the coldest that we are throughout the entire year, at this time we are about 2 million miles closer in our orbit than we are here during the summer. So yeah, if we were tilted towards the Sun here, this distance, maybe we're 1,000 meters, maybe even 10,000 meters tilted more towards the Sun here, but it doesn't make us closer because during summer, our planet has actually shifted to be millions of miles further away from the sun than we are during our coldest time of the year. So distance, make sure you get that in your head. Distance does not control the seasons. It's all about the intensity of the seasons. So let me explain why that is. So let's say here's our tilt. That was a poorly drawn drawing. You know what? That's so bad. I'm just gonna move on. So let's say we have the Earth here. We've got a good tilt to the Earth. So here's our equator. Here is the axial tilt. This is how we're rotating around and around and around. So as the sunlight comes in, let's say that it's winter time for us. Here's us. Yay, us. The light comes in. It's hitting here at the Tropic of Capricorn. Just abbreviate that to TOC. This is the most intense radiation. This location of the planet is getting the most heat because it's sitting at a 90-degree angle. The intensity is going to be dependent upon the angle of that light coming in. Here, the equator, I missed the equator, pretend I hit it. That angle is a little bit less. It's more of an acute angle at the equator. So here, we're going to get a higher, let's say we're measuring in our voltage. Let's say this would be 2.1 volts, and this might only be 1.3 voltage on our little solar cells. So here we're going to get less intensity because we're getting less angle here than a 90-degree angle. Now, if we're up here, this is us, our angle is a much more smaller acute angle than it is here. So we're going to get less intensity because that light is going to be spread over a larger area and more of an angle. When you have it more of an angle, we also have more reflected light that bounces off. So here we might have a small amount of reflected light. Here we have a very small amount of reflected light. Actually, it's going to be bouncing off straight back towards the sun. But the angle of light is going to determine the intensity of light for a few reasons, because one, it'll be over a smaller area, and two, there'll be less reflected light. Now, if our planet was flat, so let's say this was the face of our planet, every angle of sunlight would come in at a 90-degree angle. However, because we have this curvature of the Earth, we're going to get different angles of sunlight hitting at higher latitudes, and that is why in this equatorial region, or what we call the tropics here, we have more intense radiation during in that section than we have anywhere else. All right, so let's go back to taking notes. So here we're going to go ahead and diagram our seasons. So I'm going to make myself a little line there. And I'm going to put in our 4 seasons. We're going to start with spring, then go into summer, and into fall, and then followed by winter. All right, first let's get some terminology. We call spring and fall an equinox. Now remember these prefixes, these roots that we're looking at. We saw equator, it's in the middle. Equidistant, we're making sure our spaces are the same space apart. Equal, they are the same. When we have the word equinox, on the spring and fall equinox, we actually have 12 hours-ish of daytime and 12 hours of night everywhere on the planet. The North Pole, the South Pole, they both have the sun shining. One is having it set, the other is having it rise for the first time in 6 months. But everyone on the planet is going to have 12 hours of daytime and 12 hours of nighttime in the spring, on the east, that one day, the spring equinox and the fall equinox. All right, so spring, summer, and fall and winter, they happen every 4 months. Spring occurs on the 3rd week of the 3rd month, so that's going to happen in March. Summer is going to be the 3rd week in summer. Fall will be the 3rd week in September, and winter will be the 3rd week in December. So these numbers I put here, this represents March, the 3rd month, the June, the 6th month, September, the 9th month, and December, the 12th month. You don't actually need to know the specific days for us, just know the general time of year, and then it's, you know, in later in the every month here, starting at the 3rd, and then 4 months of that, and I mean every 3 months off of that. Okay, so let's go ahead, draw yourself a nice circle on each one of our seasons. We're going to draw a diagram of these as if we are looking at the side of the planet where we see night and day. So go ahead and draw in your axial tilt. We're going to draw them all the same so we can see what they look like during different times of the year. Try to make them actually in the middle, unlike mine. Fail. Okay. So here, your equator should be equidistant. Should be right in the middle, so make sure it's also a perpendicular line to your axial tilt. Go ahead and outline your equator there. And then I'm going to go ahead and put in your Tropic of Capricorn and our Tropic of Cancer. I always remember that the Tropic of Cancer is in the Northern Hemisphere because there are more people in the Northern Hemisphere, and I think of the sun's rays giving us cancer. So I think people get cancer, so obviously the Tropic of Cancer is in the Northern Hemisphere. I didn't say it made sense, but that's how I remember it. Okay, so for spring and also fall, the sun's most intense radiation is going to be sitting right there on the equator. So you're going to make that arrow, and we'll say sun's intensity, maybe, I don't know, intensity. I'll say sun's highest intensity. Ruined. None of you can probably read that. It says highest intensity. All right, it's going to be here located on the equator. So here, let's just make a note here at the bottom that the sun's intensity, I'll say SI, is on the equator here. And that is true for spring and fall. So I'm actually going to denote that here. Now, for those of you who it's going to really bug to make these the same, you can actually make this a mirror image and put the sun's energy, the most intense radiation pointing here, the equator on this side, but I got issues, so I want to put it over here. So my most intense radiation here is going to be hitting on the equator in fall. Now remember, it's equinox, 12 hours of night, 12 hours of day. So we're going to color actually along the axial tilt, and everything over here is going to be in nighttime. And everything in front is going to be in daytime because it's facing the sun. So here, I'm going to do the exact same thing for fall than I have done for spring. Now during the summertime, we have moved in our orbit. So the most intense solar radiation is now sitting here, making a 90-degree angle at the most intense radiation point, which is the Tropic of Cancer. Both my parents actually have cancer. There's a happy thing for night now. You're welcome. Anyway, so here, this is our Tropic of Cancer. Now I'm going to draw 2 more lines in here. This is the Arctic Circle. This is the Antarctic Circle. Neither of them has fries or shakes. So what we're going to do here is these lines denote the location where the sun is not going to rise or set, at least for one day of the year. It's also going to be helpful for us to be able to draw our day-night shadow line. So here in the summertime, the day-night shadow time is actually going to start here at this point in the bottom left hand on the Antarctic Circle, and it's going to go all the way to the tip top, this part on the Arctic Circle. So we're going to connect those dots right straight through the equator. And then sometimes when you're identifying these, it's going to be hard on the exam because you'll be like, I can't tell. They all look like they're just half empty and half full. One student actually told me something that really helps him is he takes a piece of paper or his hand and he puts it right on the equator. And then now he has like a pie chart that's easy to see. And he says, okay, if there's more light in the northern hemisphere, it's summer. And if there, if my pie chart's very small in the darkness, then that's summer. And so, and he also can see it the other way. If he puts it right out there on the equator, then he says, oh, there's a lot of darkness in the southern hemisphere. That must mean winter. So for him, that works really well. And if you put it here on here, it's equal. So that would be an equinox. It's either going to be fall or spring. And without more information, you're not going to know. You just have to, choose fall or spring. Okay. So here, we're going to skip over to winter. Wintertime, most intense radiation is not going to be up here. It's not going to be at the equator. It's going to be shining down. Most intense radiation, right angle, 90-degree angle, is going to be shining down here, solar intensity at the Tropic of Capricorn. Sometimes I accidentally say Cancercorn, but it's Capricorn. All right, so now the light's down here, so we're going to see a lot of sun radiation here. Going to have low angles of light up here, very, very dark. So let's go ahead and dot in our Arctic Circle and our Antarctic circles. Now my axial tilt's not quite in the center, so that's going to screw this up a little bit. But, so my light's right here, so I can see light here. So I'm going to do my dot over here. I'm going to go to my Arctic Circle up here. And that is going to be my day-night shadow. I'm going to color that in there. When I come back, we're going to draw another diagram. That's very, very similar to this, but while the planet is in an orbit, so we can kind of understand how that is changing and moving. But right here, when we were in our experiment the other day, we looked at the hours of daylight for 3 different locations on the planet. One of those locations was Ecuador, which is right there on the equator. And it was confusing to a lot of you because you're like, why do they have 12 hours of daylight? Why do they have 12 hours of nighttime every single day? It doesn't matter what day of the year it is. These diagrams kind of show you that. No matter where our day-night shadow is, if you look just at the equator, no matter how this light shadow is, no matter what phase of a condition it's in, we have equal line here, equal darkness. Equal light, equal darkness. Equal light, equal darkness. Equal light, equal darkness. So right there, that kind of helps us understand, okay, they're getting this dark time and that would be called nighttime and daytime because of this reason. Now also we looked at Barrow, Alaska. Barrow, Alaska is pretty high up on the planet, so it gets several days, and more than several, about a month and a half of darkness. So that's during the winter time. So if we look in the winter time, Barrow, Alaska, let's see if I can get, this is so dark I don't think I can get another color out here, but Barrow, Alaska would be about right here. So as the Earth spins, there's no rotation that this planet is going to do that's going to allow this place on the planet to see light. And if we go to summer here, let's say we're here in Barrow, Alaska, there's no rotation here that's going to allow the sun to set. So here, the sun, instead of going across the sky like we would normally see it, it's going to actually circle the sky. It will never be high up in the sky at noontime. It's always going to be just circling the horizon during the summer. And it doesn't go down. It just goes around and around and around it goes. All right, so get that in your notes. Make sure you understand this because you will have to identify diagrams like this on the exam.